Next, I'd like to introduce our next speaker, Dr. Spencer Dutton. And Spencer is a scientist at Lawrence Berkeley National Lab who completed his doctorate at the University of Nottingham. His research at the lab includes modeling the potential energy savings of low energy cooling strategies, including natural ventilation. Spencer assesses how ventilation strategies affect human health outcomes and model development of various novel HVAC systems and control strategies. And Spencer, I'll hand it right off to you.
Well, thank you, everyone. My name is Spencer Dutton from the Lawrence Berkeley National Lab. I am the co-PI for this project, along with my colleague, Brett Singer. And today I'm going to be talking to you about some of the exciting work we've been doing in developing new all-electric HVAC systems with integrated thermal energy storage. The idea being is that we can use this thermal storage, as Ian mentioned, to shift HVAC energy use from peak high-cost periods to off-peak periods, or periods where we have available renewables. The focus of our work so far has been on the development of the simulation tools needed to design and develop the controls for these complex systems, and then physical demonstrations where we can learn how to actually put these things together and make them work. If you have any questions after this presentation, please follow up with me via the email there. As I suspect everybody here is aware, comfort conditioning of buildings in the US and the provision of hot water account for a significant fraction of the CO2 emissions associated with US buildings. Of those emissions, about 45% relate to burning fossil fuels on site. So decarbonizing this energy use will require both mass electrification and load shifting to align with renewable generation. Heat pumps, as Ian mentioned, will be essential for that mass electrification of heating and domestic hot water. However, shifting all of that on-site fossil fuel consumption onto the electricity grid will present its own challenges, including potentially overloading an already stretched grid. So the solutions that we've been developing at LBNL are grid interactive HVAC and hot water systems with integrated active thermal energy storage that utilize new phase change material-based batteries. This technology has the potential to enable the electrification of heating and hot water systems, but also to advance the broader national goals of developing these grid interactive efficient building technologies. Supporting broader use of renewables by enabling more on-site utilization, thereby helping to improve grid and building resilience. And finally, reducing building energy use costs and emissions associated with that energy use. So the team tasked with this mission is a broad collaboration of scientists, HVAC engineers, programmers, and consultants, led by the Lawrence Berkeley National Lab, with support from UC Berkeley, UC Davis, and consulting support from Eminent Systems and a consultancy called Nestworks. So at the heart of this effort are this new generation of phase change batteries that have been developed by Sonamp, are relatively low cost. They're non-flammable, non-toxic, and have been tested to about 60,000 charge-discharge cycles with minimal degradation of performance. You know, compared to an electrochemical battery, that's significantly higher. Additionally, these batteries do not require rare earth materials that are and so they're not constrained by the limitations on lithium-ion battery production capacity. Not that I'm proposing that we eliminate electrochemical batteries altogether, because electrochemical batteries do have a role here, but I think ideally we need to take advantage of the strengths of each. So our concept was to take advantage of this new technology to develop packaged, hybrid, all-electric HVAC systems for a range of different applications and climates. And we explored combinations of current state-of-the-art HVAC technology in conjunction with this thermal energy storage to see what combinations made the most technical and economic sense. The vision wasn't to create like a Frankenstein system, but one that if we packaged it together as an integrated, then mass manufactured unit, it would be both technically and economically viable. We focused our work on, three core areas that each address barriers to future commercialization of this concept. So working closely with our industry partners, we've developed system concepts for a range of different commercial building applications, and then identified commercialization paths for one of those concepts. We developed the foundational modeling tools that will enable us, well, first us, and then the broader engineering community, to model and evaluate these hybrid systems. And then we use those models to develop and test the complex controls that those systems rely on. So finally, we put these efforts into practice by developing 2 prototype systems. The first targets small commercial buildings and the second residential buildings. So the following few slides are just focusing on our commercialization efforts. So one of the first things we undertook in our project was to participate in DOE's I-Corps program. I don't know if you've ever heard of it, but the I-Corps is an intensive 2 months training where researchers partner with industry mentors to define technology value propositions, conduct customer discovery interviews, develop viable market pathways for their technology. The idea is that researchers return to the lab primed to engage with their industry partners, and it trains those researchers to think about the technology's future path to commercialization rather than being in their ivory tower, just inventing what they want to invent. So we developed these 3 case study applications of this technology concept in partnership with our industry mentors. One of these concepts was for big box retail, one for small and medium offices, and then a system designed for multifamily residential applications. I don't think we have time here to go through all of these systems individually, but they're well described in the paper that I've referenced here, towards techno-economic analysis. We're working on several other papers, so please check in with me about those. However, it's important to explain that the designs that we're showing here have multiple different technologies, which during economic analysis, which I'll talk about later, may be excluded depending on the climate and the application, whether it makes economic sense to actually have all these bells and whistles, or whether a subset of these systems makes sense. The performance of these case study applications were modeled using our simulation design tools, which I'll be talking about in the next few slides. So we developed, one of the key challenges to modeling these systems was lack of good component models for the phase change material-based batteries, air to water heat pumps, and our heat recovery unit developed by Sealy that we're exploring. To address this, we first developed performance data sets for these component technologies, and then used that performance data to build component models. So we've successfully completed a detailed characterization of 4 different phase change material-based batteries, one with melt temperatures of 136 degrees Fahrenheit, one at 108 degrees Fahrenheit, targeting heating and hot water systems, and one at 109 degrees Fahrenheit aimed more at radiant heating, and then finally one at about 52 degrees Fahrenheit that's intended for cold storage, for cooling, obviously. And then we evaluated the performance of Sealy's innovative heat recovery unit in the UC Davis Western Cooling Efficiency Center's test chamber. That is a heat recovery unit, but it also has one pathway that it has indirect evaporative cooling. So you can recover energy, and then you can also provide some additional cooling benefit. And finally, we collected performance data from our LG, or we are currently collecting performance data from our LG heat pump in our residential field deployment of our prototype system, or our prototype system. This data will be used, once we have enough of it, to update our heat pump models, component models. These individual component models have been used to then model these 3 applications I talked about in a parametric simulation tool, which will be available to the public. This is our parametric simulation tool. We can use this tool to explore a huge range of design options, including which technologies are included and the relative sizes of these components. With a hybrid system, there are more design and sizing trade-offs that have an impact on performance and cost than, say, with a conventional system. For example, you might want to trade off having a smaller heat pump with a larger thermal storage if, say, you, for example, are limited in your electrical capacity, as Ian mentioned earlier. We can use this tool by exploring the cost savings and equipment cost implications of these design choices. This is really incredibly powerful, and we've used this as the basis of the paper that I mentioned, and we're working on several more papers related to this work. From that paper, here are some simulation results. So this gives you an example of the operational performance of one of these systems. So this plot compares the electricity use for a baseline all-electric system compared to the electricity use of our hybrid HVAC with integrated thermal storage. The blue shaded region shows the periods where our system is controlled to charge, and the dotted lines, and the pink shaded regions show periods where our system discharges thermal storage. The dotted lines denotes periods where we have peak electricity prices. So as hopefully you can see, the operation of the system is charging during those off-peak windows and then discharging during those on-peak windows, resulting in a dramatic peak load reduction. Those peak load reductions would be the difference between the yellow line and the purple line, but within that pink region. So we've been able to use these simulation tools, not just to assess performance, but also to develop the control strategies that we're testing on our prototype systems. So the next two sections are focusing on our prototypes, starting with our residential system. So over in Massachusetts, this installation includes two large thermal batteries, kindly donated by SunUp, and an LG air-to-water heat pump that uses R32 as a refrigerant, donated by LG. That unit is currently not sold in the US, but we were able to get that through that partnership. On the Massachusetts site, we're taking advantage of an existing radiant heating system to provide space heating for several zones. And then for some other zones, we're using powerful DC fan coils that will deliver heating and cooling. Performance data for this system will be collected, processed, and then displayed live using SenseWare data acquisition suite of hardware and software. As you can see here, we've got the SunUp batteries. They're relatively easy to install. They are incredibly heavy, but not unmanageable. And you can also see there in the photographs on the right that we've got our LG heat pump installed. And here, photograph, you can see this is in the basement of this Massachusetts house. As you can see, we've got our SunUp batteries installed in the basement, along with the distribution system. Most of the heat will be disseminated, as I said, under the underfloor heating system that you can see there on the right-hand side of the left photograph. And then that, on the image on the right, you can see the low voltage DC hydronic fan coil, which I think is it's a neat and an aesthetically pleasing solution. So the next section is on our commercial building prototype. Yeah, we've built a prototype targeting small commercial buildings that we can use to test their operational functionality in the field. So the key features of this are that it will have either hot or cold or both thermal energy storage. Those are relatively easy to reconfigure, and we can have up to 24 kilowatt hours of thermal storage capacity. Just for some context, 24 kilowatt hours is roughly equivalent to what you would store if you were storing heat in 120 gallons of hot water. But of course, because the SunUp batteries use phase change material, it stores that energy as latent heat in addition to sensible heat. The batteries take up approximately a quarter of the volume of an equivalent water tank. As you can see here, with the real thing in our lab right now, we have just installed the smallest capacity batteries, and the siding is yet to be added. I was thinking of going for like a brushed steel look, maybe like a Cybertruck or something. That's what I was hoping for. And you can see there the photograph. There's the heat pump. There's our balancer plant, and on the bottom right there we've got our PLC-based controller. The controllers there are sort of overkill for what you'd really have in the field, but we want the ability to implement a wide range of different control strategies. So finally, we hope to be able to test this in a small office building at LBNL in the coming year. So the final configuration would look something like this, with the fan coil unit on the actual building, replacing the wall-mounted unit that's currently there, and the thermal energy storage and the heat pump would be on an adjacent pad. Well, I want to reiterate here that ultimately, if this were to become a mass-manufactured packaged unit, these would all be in a single unitary system, not sort of spread out like this necessarily. That's the concept. Thank you. I'm ready for questions. What do I do about questions?
Much, Spencer.
Yeah.
Looks like so far we have a few comments, but I think it might be related back to Ian's talk. Let's see.
Okay.
There was a question that just came in now regarding envelope upgrades.
Okay.
And the question is, while customers don't see the difference in water heated by a gas unit versus a heat pump, they definitely feel the impact of envelope improvements, including double or even quad paned windows, draft sealing against air infiltration, and wall, floor, and attic insulation. So this is a comment. It seems like sometimes these can be an easier sell than electrification. Do you have any thoughts about that?
Not really. I think that would be a good question for Ian. But if there aren't any immediate questions, what I can do is I can talk about the sort of modes of operation of this sort of system that we have been developing. And ultimately, it would look something more like this, as a package system where, for example, you can use the heat pump during those off-peak periods to charge, during the winter mode of operation, to charge to store heat energy, and then later on, sorry. And you could also alternatively use the heat pump to store cold thermal energy. And then you can imagine a scenario where you then leverage just the heat pump itself to provide space conditioning, or alternatively, you can provide cooling to the space, for example, or you can use these in conjunction with ventilation heat recovery. These are the concepts I wanted to sort of show. I have a few additional slides if there are no further questions.
One question came in. So what is the base material for the phase change materials? It's
a secret. No, it's not really. It's the main ingredient is, I think it's a salt hydrate. I keep trying to remember the name, but it's a long chemical name and I keep forgetting. But it is it's, if you look up if you research Sunamp's hot thermal battery, it's publicly available. The key to it is not necessarily the actual sort of phase change material itself. It's what they have done to address the challenge of supercooling. Supercooling is this issue where if you see the plot on the left here, this shows us charging a Sunamp battery, and as you can see, with the temperature of the fluid going down is going down and down and down and down as it passes through the battery. And what ends up happening is you can see that the temperature of the fluid actually has to dip below that 11 degrees C temperature that the battery should be freezing at in order to trigger the nucleation, the freezing of this thermal battery. And this is a challenge for phase change materials in general. And what Sunamp have been able to do is to create these mixed within the actual salt hydrate, these nucleation agents that suspend, because they're at the same density as the salt hydrate, suspend throughout the homogeneously throughout the phase change material, reducing the effect of this supercooling, which is this fact that you have to go way below the actual freeze point temperature. I don't know if that answered the question or not.
Well, the few comments that came up as you were explaining that, Dre has said that it's, I think this was in response to the base materials, sodium acetate trihydrate for the hot batteries.
Thank you, Dre.
And someone else said, looks like a ERV thermal core, is it?
I don't understand the question, so can you repeat it?
I think this was in response to this. They said that it looks like this is an ERV thermal core.
No, it's not. No, I think what he's referring to is the heat recovery unit produced by Sealy. That it doesn't have a thermal core in it. It's essentially it's like a parallel normal heat recovery unit, really. But within one of the channels, you have the ability to inject moisture, vapor, in sort of a droplet form, which then vaporizes, and as a result, you end up with you end up increasing the moisture content of the exhaust air. But during that heat exchange, that coolth is essentially transferred to the incoming air pathway. So there's no thermal core in it. I can talk a little bit about some of the systems here that we looked at. So one of the concepts was for the big box retail store. So the concept being that you'd have either hot or cold, depending on the climate, energy storage, potentially an evaporative cooling unit that would work together to provide either chilled or heated water with glycol in it that would be distributed on the top of the roof to these smaller fan core units. The reason why we'd have it on the side here as opposed to on top of the roof is because we need to adjust the challenge of the weight of the phase change material. So the weight is coupled to the ground here. And then
one person asked, how can our students help build and test this?
come and work for the Lawrence Berkeley National Lab. I mean, if you want to reach out to me and you have students, and I'm assuming this is a professor or someone from a university facility, if you want to reach out to me, we have student positions through various universities. We have internships. We have affiliate programs. If the student is a PhD candidate, we can work with them on a longer project, and we have postdoc positions.
Thanks for mentioning that, Spencer. By the way, for the audience members, we have 2 representatives from Berkeley Lab's Workforce Development and Education team who are currently in the Berkeley Lab booth, and I just checked, they're available to talk to you now. Don't run away just yet, so that we can go through these questions. But after these talks and in a break, please do stop by. They have great opportunities available there, and can share them with you. Lots of questions are coming up, and I'm going to maybe skip around, and anything that's not answered, hopefully, Spencer, you can stick around and type in an answer in the Q&A and chat too. We do have minutes left, so we'll see what we can get through. Let's see. So the next question is, has any research been done to eliminate water as a distribution fluid and use refrigerant directly?
Really interesting that you asked, actually. So yeah, we wanted to explore that within this project, and we have made some inroads into some modeling of how that would affect our system. We didn't get at this point to, and we won't within the scope of this project, get to include models that have refrigerant distribution. I think refrigerant distribution makes a lot of sense in some contexts. Water has its advantages too. It's relatively easy to as you saw in our residential application, we could have the water go into the underground heating system, underfloor heating system, we could have the water go up through the house, all the way up to the areas where we have these DC fan cores. But yeah, there's some other sort of efficiency advantages of having refrigerant, and so future work, I think, will have systems that, when integrated, go from the heat pump via the refrigerant loop, and then have that go through the heat exchanger directly into the phase change material, as opposed to having the current system that the way that we've configured it, mostly for convenience and the fact that we can't build those types of systems. We can only piece the systems together because we're not a HVAC manufacturer. We're a national lab. So the way that we have done it is off-the-shelf components that we could plug together in using water as our transfer medium. But yeah, if you were to build a package system, it's likely that the transfer of energy from the heat pump to the actual thermal storage would likely be through refrigerant. And then you can make one final addition. You could then potentially transfer that energy from the thermal energy storage to either your fan coil or wherever you're distributing that, again via refrigerant, if that was helpful. Good question. Thank you.
Thanks, Spencer. Going back to the question about students, helping students with building and testing this, I just want to comment that Dre, your colleague, had mentioned that we might be able to put together some sort of technical training for these thermal storage technologies. So if it's possible, you know, if you guys want to connect, then maybe you can do so in chat or reach out somehow to facilitate that.
Okay.
Let's see. So another question is, do you envision these phase change materials could be DIY installed by residential consumers? And other than the weight, what are some concerns?
So the particular batteries that we've been using in our demos, the only reason we chose those is because they were already commercially available and well tested. They're commercially available in the UK and some other non-UK countries, and they are coming to the US shortly. Typically what happens in the UK is they're not generally customer installed. They're generally installed by a plumber. I myself have been, as a non-plumber, have been installing these systems using PEX, using push to fit connections. It's easy. Yeah, it's really sort of a, like, I think, a mental hurdle that people might face, like, oh my God, I can't do plumbing, but it actually it's not super difficult. So in theory, yes, it's totally DIY-able. And the fact that you're using water as opposed to refrigerant also makes it a lot easier for DIY applications.
We have a few more minutes, and there are some questions too about cost.
Yeah.
And the same audience member also wanted to mention that I think you had a depiction. This is related back to maybe the ERV thermal core that was asked earlier. I think they mentioned that there is a core in the heat recovery unit in one of the depictions that you had.
I don't know what a thermal, I don't know what it means by thermal core, or they mean by thermal core.
Okay.
So I don't know what that is.
If that audience member wants to elaborate or have, you know, on their question, then please do put it in chat. A couple questions about cost. Yeah. What's the cost per BTU, per size? What's the cost?
Yeah, so I mean, currently, here's the thing, like the thermal batteries that they're producing in the UK, they come in a variety of sizes, and the larger the batteries, the lower the effective cost per thermal kilowatt hour. I don't know exactly what the BTU equivalent is of the various different sizes that they have, but the range in costs range from the very largest systems. It works out to be around just over $100 per thermal kilowatt hour. And in the smaller systems, it's more like $350 per thermal kilowatt hour. You've got to remember that this is sort of like very early stage. This is not mass manufactured. We're talking like lithium ion like 15, 20 years ago. So I think with like mass manufacturing of these systems, there's no reason why these can't be dramatically cheaper than lithium ion, of the order of like $50 per thermal kilowatt hour. It's really a sort of a non-toxic, inexpensive like salt hydrate in a box, where the box has a heat exchanger in it and some vacuum insulation around it. So you can imagine a scenario where if you had a thermal gigawatt factory, a thermal giga factory for these things, the costs would be dramatically less.
Spencer, thanks so much. We are at the end of your time. I think there was one remaining question. Hopefully I got the others. If you don't mind answering that in chat, if you can stick around, that would be great. So thank you so much. I appreciate it.
Thank you.